Question 4 continues the theme of enthalpy changes and starts off with a calorimetry calculation. So we're given an equation, sodium carbonate reacting with 2 moles of hydrochloric acid, and we're told that in the experiment that many grams of sodium carbonate is added to 50 grams of 2 moles per decimeter cubed HCl, which is in excess. So what that means is when we scale this up to a mole, we use this value here because that's our limiting reagent. We're also given the temperature rise is 5.5 degrees. Calculate the enthalpy change for the reaction in kilojoules per mole, and we have to give the answer to 3 significant figures. So it's a Q equals mc delta T calculation, and so the M is the mass of the solution, in this case whose temperature is changed, so that's going to be 50 plus the 3.18 that's gone in, so the total mass of the solution is 53.18 grams. That's multiplied by the delta T, which is 5.5, and the specific heat capacity of water, or the solution in this case, which is 4.18. And so that comes out at that many joules. Remember, this comes out in joules at first. Best thing to do straight away, turn that into kilojoules, because we've got to have our answer in kilojoules. And so now we need to do the scaling bit. So we work out how many moles of sodium carbonate we used. So that's the mass over the MR, and that comes out at 0.03. And so the enthalpy change, the kilojoules per mole, so if you think about the units of delta H, kilojoules per mole, so it's the Q divided by the moles. That minus sign's there because this is exothermic, temperature's gone up. There's the numbers, and it's coming out at minus 40.6 recurring. So to 3 significant figures, that's minus 40.7. So there's my scribble there about why we need to use the moles of sodium carbonate, because it's the limiting reagent. Quite a complicated looking calculation now. We're going to use a Hess's law cycle to work out the enthalpy change of formation for something. But it starts off with a definition. What is meant by the term standard enthalpy change of formation? We must quote the standard conditions. So it's the enthalpy change when 1 mole of a substance is formed from its elements or constituent elements at 298 Kelvin, 25 Celsius, 100 kilopascals, or that's 100,000 pascals, or 1 atmosphere. Write the equation, including state symbols, for the reaction that represents the standard enthalpy change of formation of NH4ClO4 solid. So we've just said in our definition, it's the enthalpy change when 1 mole of a substance, so there's the substance formed, and the elements that would be used to make that would be O2, N2, H2, and Cl2. And of course they're all gases. And we must balance the equation for 1 mole of product formed. So it balances like that. And here's the sort of awful looking calculation. Calculate the enthalpy change of formation of NO using the data above. So if I just leave the screen there, I'll just talk through this. So this is an enthalpy change of formation cycle, because all the data in the table are enthalpy changes of formation. So when I do these, I always just put an elements box at the bottom, and then I have the equation that we know the enthalpy change for, and that goes across the top. And then we connect the elements box to the chemicals in the equation, and these represent the enthalpy changes of formation. So we know the enthalpy change of formation of for this here, remember that for 1 mole is minus 295, and so we've got 3 in this equation, so we've got 3 times minus 295 there. We've got 1 mole of aluminium oxide formed, so we've got minus 1676 here, minus 704 for the 1 mole of aluminium chloride, minus 242 times 6 because we've got 6 moles of water formed, and we've got 3 moles of NO. That's our unknown, so this is the well, I'm saying 3x here. And we also know the enthalpy change for this reaction is minus 2677. So I'm using the two different colours to represent the two routes. So route 1, the pink route, starting with elements, you can make the aluminium, or I haven't explained, there's no arrow there because the enthalpy change of formation for aluminium is 0, because you would be starting from aluminium to make aluminium, so there's no change there, of course. So the pink route is the 3 times the minus 295 plus the enthalpy change for this reaction. And Hess's law states that that equals the sum of the enthalpy changes for the other route. So that's all these orange ones. So there's the sort of line, the equation there. We need to rearrange this and get 3x on its own. So 3x ends up coming out at 270. And so to divide by 3, that gives us the x, will give us 90. So the answer for the enthalpy change of formation of NO is 90.